So there was a request to do an example which is not quiver. So let's pick case SUN with lambda k of the fundamental. And also we will do symmetric. So what we need to do is to pick a basis, so a basis of weights. And for SUN, it's simple. You have P1 to Pn. And we need to look at this formula here to delta. So for the fundamental, will be what we apply in the formula over there. We have M over all the weights. So the weights for the fundamental of presentation are just those guys. So we will have a sum M I from 1 to n. This is an absolute value. So we've seen this for fundamental, we've seen this contribution. So that's this contribution. And then you have the sum for the roots. So the roots of SUN are EI minus EJ. I and J go from 1 to n. And so when you do this sum over there, you get minus MI minus MJ. Right, so this thing here, MEI at the bilinear form just gives me MI. Okay. So we did this, and so this is the formula for the fundamental.
That's for any set of weights, L1 to Ln, for any
E.
Oh, E1 weight, yeah. For any.
That's for SUN.
That's right, sure.
SUN with this weight fundamental. So with the symmetric K, it's a simple generalization. So what you'll do is to see it's here. So the weights of lambda K fundamental is the set EI plus EI1, EI2, EIK. And each I goes from 1 up to n, but because we are looking for an antisymmetric, I need to put a condition that I1 is less than I2 less than the last one, IK. And for the symmetric product, just a second, it will be the same thing, but with equal. Yes.
I think the minus four is calculated by all roots. Calculated by all roots. So I think the sigma symbol about today should be hidden in front of
Yes, it should be, thank you. Yes, so it should be here sigma,
INJ.
the INJ. And you could also turn it into I less than J with factor 2.
Oh,
Right, so those are the set of all possible weights, and as a result, the contribution will be correspondingly be 2 delta of m. It will be the sum, and now I need k indices, I1 less than I2 less than IK of this sum mi I1 plus mi2 mik. Right, so that will be the matter contribution, and the gauge contribution will be just the same. So let's write it 2I less than k mi minus m. Right, so it's quite straightforward to generalize. To any representation, right? You just need to make a list of all possible weights, and then use the natural bilinear form for weights and co-weight, and you'll get the corresponding expression. So this just goes through. I mean, if you want to do it for P7, then you just pick the convenient basis and do it for P7. Okay, so that was for non-trivial representations. For quivers, life is easier. You only have a fundamental representation and adjoint, and maybe second rank symmetric, second rank asymmetric. So, the computations for delta are quite restricted. But every other point here continues just the same. Okay. And any questions? So with this information that we have, it is possible to compute the Hilbert series for the Coulomb branch for any choice of a gauge group and any choice of a representation. But we need to be careful. We look at this expression over here. There is a positive contribution and there is a negative contribution. If this contribution is big enough, bigger than this, then delta becomes negative. And if I look at the formula over here, then I have a negative power of t. But the assumption is that I have only positive powers in t. And so for cases where this is negative, the multiple formula fails, right? So it has to be strictly positive. So delta can be, must be non-negative, and if it is zero, it's only for the case where all m's are zero. Condition,
So it is not meaning.
say it again?
It is not meaningful for n.
It's not, yeah, I don't know how to give it a meaning. I don't know how to give it interpretation. There are some claims that you could extend it, but I'm not sure how to explain it.
You can outline a simple example. 2H.
Yeah, we can do this. We already did it, actually. So K1, K2. And then if you do it just like that, you're going to get into trouble. Why is that? Oh, it's because of this. So yeah, so well, you are right that if you add framing, then it will be fine. And 1, 2. There's possibly one exception if you take 1, 1 here. 1, 1, the Coulomb branch is computable. And can you tell what is the Coulomb branch? Yes, very good.
To add that.
It's just two one with one flavor, and this is the case we already treated before. Right. So, but good observation. We could actually extend it. So, for a Coulomb branch of a finite dimensional thinking diagram, with Coxeter labels or with dual Coxeter labels. Is h to the power h hat minus 2.
That's the full code.
Yeah, so this is A2. The dual Coxeter number is 3. And so I put 3 minus 2, that's H. But so by the same token, let's take an example. Which thinking diagram is this one? This one.
Oh,
That's 12. Which has 12.
H4. It's minus 2, not minus 1. Okay. This is the thinking diagram for D4.
So, they know they don't.
They know it, they just don't know
Yeah, they know. Remember my other, I think, okay. The diagram, linking diagram, metric.
Yeah, so you just apply all of the rules that we said in order to compute the Coulomb branch of this quiver, and you will find that the model space is a copy of it.
With the rule constant, I think.
Okay, any questions? Over there? Thank you. So now you wanted to do an example here. Yeah, so I'll have to take this thing and I'll start from the beginning. So the gauge group is the product UK1 times UK2. The representations that we have are three of them, 1, 2, and 3, three edges. And now I need to find the weight lattice. Right, so what is the weight lattice? Since I have the product, I'll have a collection of magnetic charges Mi here and Mi prime, Mj prime. Well, let's call it M alpha to make a difference, prime. Okay, giving names is a challenge. And now I can take, so that's the dual weight lattice. The weight lattice is just a collection of E's, what we said over here. So there will be a collection of EI, E1 up to EK1, then E1 prime up to EK2 prime. So those are the weights. The dual weights are the M vial group. So the vial group is the SK1 and then SK2. The permutation group is K1 elements and another permutation with K2 elements. Levy subgroups, that's going to be hard to write down because I need to list all possible partitions. Let's compute delta. So 2 delta of M, and then now it's a function of M and M prime. I need to get contributions from the matter, so I'll have 3 different contributions, 1 per each line. Okay, so there will be some of a bifundamental. So here on this side, I set all of the background magnetic charges to 0. So I will just get the contribution of N1, which I'll take outside. And here I'll have all of the weights of Mi. Like that. So that's the first contribution. And now we do the line, this line here. So I'll have sum I from I to K1, and another sum alpha from 1 to K2, and Mi minus M alpha prime. Okay. So here I have K1 contributions times N1, which is just the product of those two. And here I have K1 times K2. So K1 times K2 different contributions. 1 per each hypermagnet. Right? Here there are K1 times K2 hypers, N1 times K1 hypers, and here K2 times N2 hypers. So I'll have another contribution, which is N2 sum alpha from 1 to K2 M alpha prime absolute value. So 3 matter contributions, and the generalization to any quiver is 3. Okay. The main issue will be with giving labels. And now I need to get the contributions of the gauge sector. There are 2 gauge groups. So I will have -2 sum I less than j mi minus mj. Those are the positive roots of UK1. And then there will be a similar contribution, sum alpha less than beta m prime alpha minus m prime beta. Any questions? So now we are done, right? Contributions for all edges and contributions from all nodes. Positive and negative. There are 2 fugacities here. So there will be Z1, and Z1 will be to the power sum mi. Right, so this is J, what we call J. And there is a Z2, one for this and one for this. What else? The dressing factors are, as we said, for 1 gauge group, so there's no point in repeating it. And that's it.
Yeah, the dressing factors only.
Yeah, they don't. Yeah, the conditions on dressing factors are that they are equal. So when these 2 are equal, they don't know about the other.
No, they don't know.
When the m's are equal, they don't know about the impact, just independent. And that's it.
So when you do the sum, you have to be careful about and also the bias element.
Yeah, when you restrict to the while group, you restrict the m's to be in order and the m primes to be.
Yeah, but they don't.
They don't talk to each other.
Is there any possibility that they mix? I don't know.
No, I mean, if you look at this formula here, you could see that there will be analytic regions where 1m is either bigger or smaller than m prime, and you have to go over all cases. So there will be many analytic regions.
Maybe they could cancel each other out.
There will be the analytic behavior will change as you move from positive sign to negative sign.
So if I have multiple such gauge group, as you said earlier about the story geometry, what Marcus was doing, when I do this 2 independent sums, I can again look at positive codes. Yeah,
except that the dimension of the toric diagram is going to shoot high very quickly. The dimension is the number of charges.
So you have to take care of all the dimensions around, which is good.
Yeah. So here the lattice is of dimension K1 plus K2,
Okay.
right? So you'll have to draw a lattice of this dimension and to look at all of the vectors and to check when they change signs, when the analytic behavior changes based on this formula. So it's quite, I mean, also for a computer, it's going to be quite a hard task. You could look at the paper by Marcus and then see cases, but there in that paper, there are examples of low rank, even examples with low rank, but different representations. So even there, you could see that there is quite a complexity in the computation. More questions? Okay, so there is a family. Let me give you an exercise. Consider two, one, and one, n times.
That's the formula.
Yes. So it's a one parameter family parameterized by the number n. And so you have a central node of 2 and n nodes of 1 connected to this central node. Show that the Coulomb branch is equal to H4 for n equals to 3, D4 for n equals to 4, and compute it for n greater than 4. Okay, and D4 is the minimal nilpotent orbit of SO8 closure. Okay, it's a fairly simple exercise. Now, how would you do such a thing? So remember the exercise that I gave with the whole little root polynomials. How many sums do I have? I'm going to have n plus 1 sums, right? So there are n plus 1 sums. So the dimension of the Coulomb branch is n plus 1. That's the quaternary dimension. And as a result, I'll have n plus 1 sums. And I need to decide which sum to perform first. I could write the whole sum, but it's up to me to decide how to sum. But you could see that there are identical legs here. This contribution will be the same as this contribution. So, except that over here I have a charge. It's the background charge. Correct?
Sorry,
Well, I'm talking about a problem that was of interest before. So in order to compute this thing, you need to compute the whole little polynomial with the background charge given by the node of 2. And then sum it with a weight function over all whole little contributions. So the way to do it is to first perform this sum but this sum is the same as all other sums. So I will only have to sum over the last one,
Yeah,
but the last one will have a contribution from all of them, including the weights from the delta that depend on the magnetic charge. So that's how you do. Yesterday, I was asked how to do the computations with the whole little root polynomials in class S. This is an example for class S with whole little root polynomials.
so here you said if I have to turn on the background charge in the background mono.
It's not a background charge. These are all gauge nodes.
Mhm.
So I have a magnetic charge over here, and I have magnetic charges for each of them. Eventually, I will have to sum over this guy. I just need to decide on the order of the sum. Right? So none of them are background charges, but I can treat it as a sum with a background charge,
I see.
fix the value of the magnetic charge here, perform the sum. So that will be like doing it with a background charge. After I finish the sum, I can sum over the last one, last sum.
And that is
This requires the knowledge of the Hilbert series with background charges.
that's only possible here. Or it's possible.
Well, okay, so we can do other cases. We can look at other examples. Up to now, I refrain from erasing the monopole formula.
Right.
I will now erase the monopole formula under the understanding that we know how to do it. Okay, we won't come back.
Can leave the white and
This was the list of.
you can erase this.
Okay. So consider this quiver for affine E6. Okay. So as usual, you can apply the monopole formula, no problem. And I can compute the Coulomb bunch. Do you know what is the Higgs bunch of this? You don't? Come on. You should. So it's C2 mod T, where T is the binary tetra
Yeah, okay.
group. Associated to E6.
Mhm.
And then the Coulomb bunch. So I don't expect them to know this, but I do expect you to know this part.
Yeah, okay.
Because that was some trivial stuff from the PhD. And this is the minimal important orbit, 46, closure. Now, again, I have a collection of sums to do. In total, the sum of numbers here is 12. The quaternionic dimension of this is 11. And so I have 11 sums to perform. And I will need to do choice, which sum to do first.
So can I treat the legs independently and the sum
Yeah, so then it makes sense to leave this sum to be the last, to compute the Hilbert series for 1, 2, and 3 as background charge. And then I'll just cube it and add the contribution from the last one. And the result is a simple result. Okay.
But if the 3 will look like a
Yes. It will, I need to leave all 3 charges. I could put one of them to 0. Any questions? Any questions from the remote audience? So, and again, the similar thing, we will do all cases. So, next case to consider is 1, 2, 3, 4, 3, 2, and 1, and here 2. Which quiver is this? These are fundamental objects. They are very important. That's the reason I mentioned them one by one. Anyone, including the guys on Zoom.
is this
Yes, this is a finely 7. This is a quiver for a finely 7. So the Higgs branch is C2 mod the O. And there is an O binary octahedral group. And then the Coulomb branch is the minimal nilpotent orbit of this group. Both of them are fundamental spaces. The Klein singularity of type E7 and the minimal nilpotent orbit of type E7. Similarly here, Klein singularity and minimal orbit. They are dual to each.
if they combine it, let's see.
Well, it's straightforward. This is a minimal nilpotent orbit. So the highest rate generating function for minimal orbit set the fugacity of the highest root to be mu. Then the highest rate generating function is 1 over 1 minus mu. Any questions? So those are, you could just train yourself. You know the final result, you know the quiver, you know the monopole formula, could plug everything in and show that what you get is this.
Answer is very simple.
Answer is very simple. That's what makes minimal orbits special. One of the points. Any questions?
The formula can be used for all, you know.
Yeah, any algebra, including non-simply laced and exceptional. Yeah, if once you phrase it in terms of roots and weights, it is supposed to work for any algebra, irrespective of its type. And that's why it's very desirable. Each time you find the formula, it's desirable to work in terms of roots and weights. And that's why I told Rak-Kyeong not to use Young diagrams, because they are only good for A type. And since we are interested in all possible algebras, the use of Young diagrams is too restrictive. It's not useful. This is a major problem with the physicists in general. They learn how to work with Young diagrams, and when they make an attempt to generalize to other algebras, they get into trouble because Young diagrams no longer serve B-type cases.
With restriction.
So instead, what you do is work with roots and weights. When you do that in terms of roots and weights, you do it for all algebras.
If Young Child Lu is asking, could you please clarify what is the frequency of the highest root?
Okay, let me see. So, do you know what is the highest root?
Do you know what is the highest root? Yes, I think so.
So let's take an example. A1, okay? Then the representation with highest weight N has a fugacity, highest weight fugacity. Mu to the N. Okay, so if it's the fundamental representation, the highest weight is 1, and the fugacity for the fundamental will be mu. But if it's 2, if n is equal to 2, we are dealing with a joint representation, and so the highest weight fugacity will be mu squared. And so the expression that we have over there is 1 over 1 minus mu squared t squared. And this, if you look back to the previous lecture, this was the highest weight generating function for C2 mod Z2. That's what we wrote. Okay, so the highest weight, what is the highest root? It's the highest weight of the adjoint representation, right? So I just need to compute what it is. For every algebra, it will be something different. And then the fugacity for this highest root, I will call it with mu. Yeah, since I'm dealing with roots, the highest weight, the highest. Okay. Another example, okay, let me take A2. What's the highest weight fugacity for the root?
You need 1, 2.
mu1, mu2. Exactly. And therefore, the expression will be 1 minus mu1, mu2, is 2.
So if we add to 1,1.
Yeah, but that's it's a very simple computation. It's not a difficult computation. Just need to identify what is the joint representation for the corresponding algebra. And since we are dealing with highest weights, we are using highest weights to denote the representations, then it becomes straightforward to compute the fugacity for the joint. More questions? Okay, so we could also modify the formula for non-simply laced quivers. Okay, so here's an example of a non-simply laced quiver. Let's take the case of G2. So here's an explicit quiver. This is the affine Dinkin diagram for G2 with Dinkin labels 2 and 1. Those are sometimes called the dual Coxeter numbers. And then I want to figure out how to modify the monopole formula such that I will be able to follow through these formulas for non-simply laced edges. And what we note here is that this edge here will have magnetic charges M1 and M2, and magnetic charge, let's call it just N, or this one. Again, there are two edges, this edge and this edge. So let's write the expression for 2 delta of M1, M2, and M. So the easy contribution is from here. I will have M1 and M2. So that's for the edge. And now I have, normally if this was an ordinary edge, I would write M1 minus M and M2 minus M. But because this edge is triply laced, so this root is 3 times bigger than this root, I need to add this factor 3. So I put the factor 3 here.
They are not familiar.
So
They are not familiar.
So I don't understand why we add plus. So can you-
they don't know about non-simply laced algebras. So
But if we like,
right. So for this, we will need to talk about Dinkin diagrams. So the A type will looks like this. N nodes, which are connected on a line. Next is B. And I have nodes which are connected like that. And then the last node is a short node. Okay, this is a short node. If I compute the length of the vector using the what I raised over here, remember that we had a bilinear form. So I need to put a weight and the corresponding co-weight and to compute the length. So this guy will have a length which is shorter than this guy. So let's write down the root system. Of type B. The simple roots are written in a canonical basis, which is also arising from the brain system. Alpha 1 is E1 minus E2, which is the same orthogonal basis that we will use it for A type. And then it will go the same way for alpha n minus 1, E n minus 1 minus E n. And the last root, simple root, alpha n is equal to E n.
for A type, you saw that there. E type, just this multiplication.
When I compute alpha 1, the weight and the co-weight, because this is an orthogonal basis, I find 2. But alpha n, weight and co-weight, is 1. It's shorter.
Oh, okay.
The length is shorter by square root of 2. So going back to the case here, for G2, length squared of this node is shorter by the length square of this node by factor of 3. And for this reason, we just stretch the magnetic charge for the long root. We stretch it by the amount of the non-simply laced. Okay. So using this definition, I can now compute not just for quivers which are simply laced, I can also compute for quivers which are not simply laced. And indeed, if you compute the Coulomb branch for this quiver here, you will find that it is a minimal G2. The minimal nilpotent orbit of G2 closure. And it has quaternary dimension 3 as the quiver says. Any questions? So now we know how to extend the computation to non-simply laced quivers. Certainly, thank you very much. We will have minus M1 minus M2 with a factor 2. Right? Because this is an abelian gauge group, this is non-abelian, and so there's only going to be one positive root and one negative root. So they will contribute the same with the factor.
That's the contribution. So, contribution. Okay.
Yeah, so these two were contributions from the edge. These two contributions from this edge. And now I have a contribution from the node. This is an abelian node, so it doesn't contribute. And this is also the experience that we have in 4 dimensions when we compute beta functions. Abelian gauge fields do not contribute. In the gauge sector, we only contribute to the matrix. Okay. So now the sky is the limit. Pick any quiver that you wish and compute. It's just a question of computational time. This is why I said that because of this formula, we are able to compute Hilbert series for moduli spaces on an industrial scale. Just feed it into a computer, and you don't just put the quiver data and spit out the final Hilbert series.
If they are mathematical package.
The one that the students use in Imperial College is the one written by.
Okay, so mathematical package.
Yes, yes. So I can share this.
It's available from the door.
Yeah.
Yeah, like 10 or 15 minutes, I mean.
Yeah.
More exact, so you
I think this is in terms of examples. We have done enough. I think now it's time to exercise. So if people will not actually perform the sum, they will lose the discussion remaining part, because to specify quiver and the result of the moduli space, this is very easy. But I'm not sure if you follow. So yeah, now we are ready to compute for whole set. Perhaps the next thing to explain is the notion of quiver subtractions. Okay, any questions? This is switching gear. Okay, so in order to understand the notion of quiver subtraction, this is a more advanced topic. It's better to do Higgs mechanism. And I will just take an example of SU3 with N flavors. Now, what does the Higgs mechanism tell us? It says that if I have a gauge group G with matter R, I could turn on some vacuum expectation value to scalar fields and break the gauge group to a subgroup. But this subgroup doesn't have to be a trivial, to be a subgroup, but there are conditions. So let's suppose that G is broken to a subgroup H. Then there will be a decomposition. R equals to sum AI Ri, where the sum here, I, runs over all irreducible representation, and most of the AIs are except for few. Now, the adjoint representation will also decompose. It will decompose to the, let's say, distinguish between the adjoint representation of G and the adjoint representation of H with the capital and lowercase. Now, and then plus another sum, I, BI, R.
Small I, H, capital I.
Yeah. Okay, so then if there is such a breaking, I will be left with the new gauge group. Is H with representation which is sum. What I have is that the representations, the adjoint is the representation for vector fields, and I will need that each one of them absorbs a representation from the matter in order to become a massive gauge field. So I'll be left with some BI minus, sorry, AI, the thing which remains after I absorb it is AI minus BI times RI. And so the new gauge group will be H with representation this stuff. Except that I count representations non-negative. So I have a condition that AI must be bigger or equal to BI for any I. So it's not possible that G will break to all possible samples. There is a collection of subgroups, but only subset of them will satisfy this condition. So I need to check it one by one.
This is basically thing for any gauge field. So far, you only looked at U1 plus U1, breaking it to U1. Okay? The diamond. This is for any. Now, you can know it's simple diamond.
Shall I remind you what you know?
No. I mean,
Okay, so let's do a simple example. Let's take SU3. And let's suppose that it breaks to SU2. And now we need to check how the fundamental representation decomposes to the representation of SU2. So I'll have 2 and 1. Okay. And I also need to decompose the adjoint. So the adjoint is 8-dimensional. And it decomposes to 3 plus 2 plus 2 plus 1. So now A for the 2-dimensional representation is 1, and B two. Okay. A1 is 1, and B1 is 1, and that's it. So what do we learn from this? If I have n equals 1, only one copy, I cannot do Higgsing, because then I will violate this condition. If I'll have more than one copy, 2 and above, then it's okay. Right? So in general, if I have n copies of this, then I'll have to multiply this by n and this by n. And now the condition B A2 minus B2 is n minus 2, and A1 minus B1 is n minus 1.
The fundamental is the line. The adjoint rotate. What? Line. That is. Otherwise, I can't do it.
Okay, so we now end up with a theory. So if we do it for general n, we have a theory with n minus 2 fundamentals. The new theory is SU2. Has n minus 2 fundamentals, and it has n minus 1 singlets. Okay, so the dimension of this moduli space where SU3 is broken to SU2 is n minus 1 quaternion. So I can write it in a phase diagram where I can say, here's SU3, here's the case where I have a SU3 with n flavors. And I break it to another phase where now the phase is SU2 with n minus 2. And to move from here to here, I require n minus 1 dimensional module. Now, for this gauge theory, if I start with SU3 with n flavor, the dimension is 0. There's just 1 point. 1 point in the moduli space where the SU3 gauge group is unbroken. If I give an expectation value to a hypermultiplet, it will break the symmetry. But I have 2 ways of breaking. Either to SU2, then I have n minus 1 dimensional subspace, or I can fully break it. If I fully break it, then the dimension will be 3n minus 8. 3 for every hyper, right? So that this is what you see here. 3 times n minus the dimension of the group. Now, what is the difference between those two? Here I moved up a step n minus 1. I ended up with 3n minus 8. And so the point in between should have 2n minus 7. Right, such that the sum is 3n minus 8.
What's the line between 2n minus 7 and 3n minus 8?
We will need to describe it. Not yet.
That's like a Hasse diagram.
Yes, it's a phase diagram from physics perspective. I want to first go over the physical process. And this is what we have. And we need to explain what's here and what's here. How do I get 2n minus 7? Let's compute the dimension of this moduli space. So this moduli space, what's the dimension of this moduli space? It has how many hypers I have? N minus 2 times 2. But they hits 3 vector multiplets. So I need to subtract 3. So what do I get? 2n minus. And indeed, this is the number that we find. Sorry, I wrote it wrong. Let me erase. Sorry. This is this is 0, n minus 1. Therefore, this is n minus 1, and this is 2n minus 7. What are you asking?
That's the minus 2n minus 2.
And the gauge group, it's a Higgs mechanism. So 3 vectors become massive, and they take 3 hypers with them.
Here, it has a diagram. You do the edges. You label the edges, right?
Let's draw the Hasse diagram more clearly. So the phase diagram contains 3 points. In this point, SU3 is unbroken. and the gauge symmetry is has n flavors. On this point, SU2 is unbroken, but it has less flavors, n-2. And over here, this is the whole gauge group is broken. Let's write it like nothing. There's no gauge group. And those points have dimension. This has dimension 0. This has dimension n-1. This has dimension 3n-8. The slices between points, so between here and here, I have n-1 dimensional. And between here and here, I have 2n-7.
So n-1 I get by having n high plus n high minus 1. And
Okay, so how do we understand those the transition from one point to another? There are three phases and two transitions between them. So let's try to see what's going on. Let's first explain this thing here. This is just the moduli space SU2 with n-2 flavors. So I will write it as a dn-2 singularity. Let's write it again. Okay, so here, what I need, the gauge theory that I have is the gauge theory for SU2 with n flavors, and if I write the Higgs branches of SU2 with n flavors, this is equal to the dn singularity, so the minimal orbit of well, let's write it in a different place. Let's leave this line. And I could write SU2. Let's compute this moduli space. So what I need to do is to evaluate Higgs branch. How do I evaluate Higgs branch? Matter things, vectors, and this. So I have a matter field, which is Q. I have two n hypers, which are parameterized by complex variables with two labels, alpha and I, where alpha goes from 1 to 2. That's the SU2. It's a rectangular matrix with two entries, and I goes from 1 to 2n. Altogether, I have 4n complex number. So this is the parameterization of H2n, which is the number of hypers that we have in the field. Okay. Now I write down a gauge invariant matrix. So Mij, it's bilinear. And I contract with the invariant tensor of SP1, SU2. So I get a 2n by 2n matrix, which is antisymmetric. And the rank of M, well, the superpotential is going to be written with an adjoint on the vector multiplet with labels alpha and beta, then Q I alpha, and let me put it up like that. Q J beta, and I need to contract the I and J indices, so I'll have delta ij. This is the superpotential. So from a variation of the adjoint, I get the condition that the contraction of the flavor indices vanishes. And from this, I get that m squared is equal to 0. M is antisymmetric. Trace of M is trivially 0 because it's antisymmetric. And m squared is equal to 0. And the rank of M is at most 2 because I use a 2 by 2n matrix in order to construct it. This is the minimal nilpotent orbit of SO2. Now, if I remove this restriction, the rank here can have two choices. Be either 0 or 2. Cannot be 1. Why is that? Yes, this condition. An antisymmetric matrix cannot have an odd rank. And so this is the rank condition. And so I have two options. And therefore, if I write down the phase diagram, that's just SU2 with n flavors, right? So there are two options. Either the rank is 2 or the rank is 0. Rank 0, rank 2. The rank 0 is just one case where the matrix is identically 0. So this is 0 dimensional. And any other point, so if I have a matrix which is non-zero, it necessarily needs to have rank 2, and therefore all points are the same. And this is the set of points over here. And the dimension is what we computed before, 2n minus 3. Any questions?
I cannot follow the Y angle. You keep the two.
Everyone doesn't follow why it's not. It cannot be like wow.
Okay. Take matrix which is antisymmetric. 0, 0, A minus A. That already has rank 2.
Okay.
That's with that. Yeah.
It's a trivial point, not a big point. More questions?
Now you draw 0 and 2n minus 3, so how can we what's the link to the
Now this thing I will call dn. Okay, and here I see a copy of SU2 with n minus 2 plates. So I will call it dn minus 2. And indeed, the dimension of dn minus 2 is 2n minus 7.
If I completely Higgs that that's the difference.
So the theory of SU3 with n flavors has three different phases. There is a phase, a unique phase, a point, where SU3 is unbroken. There is an n minus 1 dimensional subspace where SU2 is unbroken, and then all other points, the biggest phase, it has dimension 3n minus 3 is minus 8, where the gauge group is completely hit. So that's the physics of this problem. We have three phases where in each phase it's the different set of matrix fields. Now let's explain this a n minus 1. So when SU3 is broken to SU2, there is a commutant U1 that commutes with this SU2. The n singlets are singlets under SU2, but they are charged under U1. So now I have a gauge theory where I have U1 with n minus 1 charged hypers. So let's write the general case. If I have the quiver, the Higgs function of the quiver 1n, remember, we said this is minimal SLN closure. And again, I have 2 points, and this is also denoted by an minus 1. Okay? It has 2 points. There is the point here where U1 is unbroken. Any other point, U1 is Higgs, and it has dimension n minus 1, because I have n hypers, and one hyper combines with a vector to form a mass single. So this slice is an minus 1, and this is indeed the root for this slice. So there are 2 types of slices, the minimal D and minimal A.
SU3 and
Exercise, it's time to stop, right?
yeah, I think it's
So exercise, compute the phase diagram of SU4 with n flavors.
okay. So are there any questions in the audience? Okay, so we can have a 30-minute break and continue at 4 with lecture number 4.
Okay.
So, oh, there's a question. Could the slices of D n minus 2 and A n minus 1 be switched, or why SU2 is first?
Well, this is not, it's not a, there's no choice. It's a computation. You could ask, well, let's suppose that U1 subgroup of SU3 is unbroken, starting from here, because it is a subgroup. And then you will see that these conditions are violated. That's part of the exercise. We could do it if you want, but maybe it's better that you do it first and convince yourself instead of me doing it. Because it's a straightforward exercise. You just do, you repeat the decomposition. Instead of SU3 going to SU2, you do SU3 going to U1. You just show that with such an embedding, these conditions are valid. So I didn't have a choice. Right? The gauge group which survives here is only SU2, and the commutant of SU2 is U1. So that must be an A slice. And here, this is an SU2 gauge group, and therefore this is a D slice.
Okay, good. So we will meet at 4 for lecture number 4.
And notice, Rak, you are asking me this question, that this is a modular space, it's a symplectic singularity, which is not an nilpotent order.
Right.
Because it has values.
Ah. Okay. Yeah, so okay, so let's meet again at 4. Okay, good.